Have you ever really thought about how your body stays at that perfect 37 degrees Celsius no matter if you're stuck in a blizzard or sweating through a heat wave? Well, it's not magic. It's an absolutely incredible biological machine doing its thing. Today, we're diving deep into that machine, the body's internal thermostat. We're going to explore how it works, why it's so vital, and even how we might be able to hack it. So let's get into it.
So what happens when that internal thermostat fails? Well, the 2004 Athens Olympics. It was an incredibly hot day, and one of the best marathon runners on the planet was just brought to a dead stop. Her body's cooling system was completely overwhelmed. It's just a crazy, real-world reminder of the high-stakes game our bodies are playing with temperature every single day.
All right, so let's start right there with the very real danger of what happens when our bodies just can't keep up and the heat starts to win.
This right here is the critical number. Once your internal temperature climbs above 40 degrees Celsius or 104 Fahrenheit, you are deep in the danger zone for heat stroke. And look, this isn't just about feeling a little too hot. This is a life-threatening medical emergency where your major organs can actually begin to shut down.
And it's definitely not just elite athletes. I mean, think about it. Anyone who's generating a ton of internal heat from their muscles while working in a hot environment is at risk. We're talking soldiers in the desert, firefighters running into a blaze, agricultural workers, construction workers. For all of them, managing body heat isn't just part of the job, it's absolutely crucial for their safety.
So, how do most of us avoid this pretty awful fate most of the time? The answer lies in a really fundamental principle of biology, this constant drive to maintain a stable inner world. The concept is called homeostasis.
Homeostasis is kind of the unsung hero of our entire physiology. It's basically the sum of all the processes that keep everything inside us, from our temperature to our blood sugar, within this incredibly narrow, perfect little range. It's what protects our delicate cells from the wild and changing conditions of the outside world. You know, a really great way to get your head around this is to compare it to something we all have. A thermostat in your home. Your house has a temperature you want it to be, right? That's the set point. Well, your body has one too, right around 37 degrees Celsius. Your home's thermometer is the sensor, and in your body, that job belongs to your brain's hypothalamus. And finally, the furnace or AC that kicks on, that's your muscles, blood vessels, and glands, all working to get your temperature right back to that perfect set point.
But why? Why is keeping this stable temperature so incredibly important? Well, the reason comes down to a universal biological rule known as the Q10 effect.
Okay, so Q10 sounds complicated, but it's not. It's basically just a rating for how sensitive any chemical reaction is to a change in temperature. All it does is tell you how much faster that reaction will go if the temperature goes up by 10 degrees Celsius.
And here's what that looks like in the real world. You see, most of the processes happening in our bodies have a Q10 of about 2. That means for every 10-degree jump in temperature, the reaction rate doubles. And that sounds great, right? I mean, faster is better? Well, not so fast. There's a huge catch.
And here's the crucial point. Your body isn't just one reaction. It's this beautiful symphony of thousands of different chemical reactions all happening at once, all linked together. Now imagine if some of those reactions suddenly double in speed, while others triple and some barely speed up at all. The whole network gets thrown into total chaos. It's like an assembly line gone haywire. That's metabolic anarchy, and it's exactly why a stable temperature is completely non-negotiable for us.
So to solve this massive problem, life on Earth evolved down 2 major paths. You've probably heard of them as cold-blooded and warm-blooded, but the more accurate terms are ectotherms and endotherms. These 2 strategies are just fundamentally different. An ectotherm, like a lizard, gets its heat from the outside world, basking in the sun. Its metabolism is pretty slow, so when it gets cold, the lizard just slows down too. But an endotherm, like a mouse or you and me, is its own furnace. We make our heat internally, which means we have a much higher resting metabolism. When it gets cold, we just burn more fuel to stay warm. So where does all this amazing internal heat actually come from? The answer is so cool because it's completely counterintuitive. Turns out our cells, the cells of endotherms, are just less efficient. They're kind of leaky. Ions are constantly slipping across their membranes where they're not supposed to be. This forces our cells to constantly burn energy, running these tiny little pumps to push the ions back. It's like we're constantly bailing out a leaky boat, and all that bailing, all that work, generates the massive amount of heat that keeps us warm.
Okay, so we've established we are inefficient,
heat-producing endotherms. Now let's zoom in and focus on the specific toolkit that we humans use to manage all that heat and maintain our own perfect internal climate.
Our bodies are always exchanging heat with the world around us in four main ways. First, there's radiation, which is that warmth you feel from a campfire without actually touching it. Then there's convection. That's the reason a cool breeze feels so amazing on a hot day. Conduction is heat transfer from direct touch, like when you hold an ice pack. And finally, evaporation, our body's superpower. It's the incredible cooling we get when sweat turns into vapor on our skin.
And the brain behind this entire operation? It's a little region called the hypothalamus. It is our master thermostat. It's constantly checking your core temperature, comparing it to that 37-degree set point, and then issuing commands. You getting too hot? Okay, it tells you to sweat and sends more blood to your skin to radiate that heat away. Getting too cold? Fine, it restricts blood flow to the skin and triggers shivering to generate more heat. It's just this elegant, non-stop feedback loop.
Now here's a really cool evolutionary tidbit. Even though we lost most of our fur, we held on to a key adaptation from our furry mammalian ancestors. In the non-hairy parts of our bodies, so the palms of our hands, the soles of our feet, and our face, we have these specialized blood vessels that basically act like super efficient radiators. We can think of them as heat portals that can dump a ton of heat really fast when we need to. And this brings us right back to where we started. We began with an athlete overheating. We've gone through the biology of how we control our temperature. So now, let's see if we can actually use that knowledge to flip the script, to turn that problem into a real performance advantage.
The question is pretty simple, but the implications are profound. If our hands are basically natural radiators, can we amplify that effect to cool down our entire body? And by doing that, boost what our muscles are actually capable of?
So some researchers at Stanford decided to put this to the test. They had people do bench presses until they just couldn't do any more. One group rested like normal, but the other group rested while using a special device that cooled the palm of their hand. The results were, well, they were astounding. The group that used the palmar cooling showed a dramatically bigger improvement in how much work they could do over time.
So, just by pulling heat out of the body's core through this natural little doorway, this radiator in the hand, the researchers were able to slow down how fast the muscles were heating up. This directly cut down on fatigue, and it allowed the subjects to do way more work and get in shape much faster.
And that leaves us with a really fascinating thought to end on. I mean, this goes way beyond just making better athletes. If we can manipulate our body's temperature so easily and effectively through these natural portals, what could that mean for treating medical conditions? Like helping MS patients who are sensitive to heat, or maybe even managing body temperature during delicate surgeries? We are just scratching the surface of what might be possible by learning how to hack our own internal thermostat.